if I were to measure my $50, okay, so let's say I've got a $50 here. And let's say that I could get not just the diameter of it, but I could get a height for it too. Let's call it h. All right, so I'm going to get a height plus or minus uncertainty in the height. And then let's say this time I just measure the radius. So we'll have r plus or minus sigma r. Let me do that here, and I'll give us some measurements, and then we'll see if we can use this technique to find the uncertainty in the volume. All right, so I think the radius I'm going to say that it is 1.50 plus or minus 0.05 centimeters. And then let me try to measure the height here. Yeah, it's right about 2 millimeters. Okay, let's just use those as our best estimate and uncertainty for each of the dimensions that we need. Now we want to calculate the volume of the $50 and give an uncertainty in the volume. I mean, the first thing you'd want is just a formula for volume of a cylinder, and then, just try to decide how many sig figs is the right number to keep. We have a formula for a cylinder from geometry. It'll be V equals the area times the height, which in this case would be pi r squared times the height. All right, and that's certainly the formula that we'd want to use here. All right, so when we're finding the best estimate of the volume, we just simply want to use the best estimate of the radius and then use the best estimate of the height. All right, now our best estimates, of course, are on the left here. Let's plug that in. Okay, and I'm getting 1.4137 dot dot dot. But how many sig figs should I keep is the question, right? So this one's got 3 sig figs. This one over here has just 2 sig figs. Leading zeros are never significant. Trailing zeros here can be, as long as the decimal is expressed. So that 0 is significant because it doesn't have to be there. It could have been written just as 0.2, and then I could have stopped, and that would be 1 sig fig. The fact that I put that 0 there means it's there on purpose. It's 2 sig figs. Now I should only keep 2 because the the 2 sig figs of the 0.20 limits our precision. Like I can't put in the end 1.41 because I'd be saying I know more than I did. Like I don't really know that volume to that precision, so I'm going to actually round it to 1.4. And then we'll put centimeters cubed. All right, that's our best estimate of the volume. Now we've got to figure out how much uncertainty there is. And you can't just say that because we had 0.05 uncertainty in the original measurements that we suddenly have 0.05 uncertainty in the volume. It doesn't work that way. Actually, we'll see that in all likelihood, it'll be quite a different number after we propagate the uncertainty through. Okay, so how do we propagate it through? That's the tough part. So we want to now find what is called sigma v, the uncertainty in the volume. And it is found with that formula that I mentioned before, which would be the partial derivative of v with respect to one of the variables times the uncertainty in that variable. And the first variable could be the radius. And then we have to do the partial derivative of v with respect to the other variable, the height, times sigma h squared. All right, that's what we want to do. 2 variables involved. Now we got to find the partial derivatives, though, with respect to these different letters. Okay, so let's find the partial derivative of v with respect to r. And then we also want to find the partial derivative of v with respect to h. All right, so you want to go back to what the original formula was. And imagine just doing a derivative, but it's a derivative where one of the variables is treated like a constant. So when you're doing the partial with respect to r, you got to treat h as constant. And when you're doing the partial derivative with respect to h, you treat r as constant. All right, so imagine it's like pi r squared times 8 or something, or pi r squared times 3. It's like, what would the derivative of that be? You leave the h there as if it was a number, okay, and you keep the pi as well because it is a number. And then since we have r squared and we're trying to find the derivative of r squared, that would be just 2r. So you keep the pi, you keep the h, and you do the derivative on the r, which becomes 2r. Yeah. Now we want to try to do it with respect to h, as if h is the variable and r is the constant. So it's like pi times 2 squared or pi times 3 squared h. What would it be then if r is the constant? What would the derivative be with respect to h? But okay, so let's say that those are our partial derivatives. It's a little bit tougher now because we have variables in our partial derivatives. Before, it just came out to a number like 1, so that was easy. Okay, now we got letters involved as well. All right, but the same principle holds. We want to plug in our partial derivatives. Okay, the only difference this time, though, is we'll plug it in. So just 2 pi rh times sigma r squared. And then we have pi r squared times sigma h squared. We can actually plug in a number for r and h, though. We just want to plug in our best estimate for these. That's all we have to do. Okay, so above, I had said that R's best estimate was 1.5 and H's best estimate was 0.2. So we just want to plug those in. Two times pi times 1.5 times 0.2. Then we got to put in our sigma R, uncertainty in the R was 0.05. Yeah. Okay. Yeah, that looks good for plugging all the numbers in. Let's see what we get. Okay, I think I'm getting the uncertainty in the volume is 0.37. This would be cubic centimeters. All right, so our best estimate was 1.4 cubic centimeters. And now we just want to put in our newly found uncertainty in the volume, which I should round to the same place value that I gave in my best estimate. So I put 0.4 centimeters cubed. As you can see, the number that you get in the end, it doesn't really have any clear relationship to what the numbers were for our uncertainties originally. Okay, so it's a common mistake for people to just take the uncertainty in the original measurements and assume that that is the uncertainty in the final result of the calculation, right? But you can see it's actually quite different. It's because what we've done is we've propagated the uncertainty through the calculation.